Welcome back, quadrature fans. My name is Professor Theoremus Antiquitus. I'm beaming this to you from 1640, and today we're going to review basically what we did, over these past 9 or 10 lectures. And so let's get to it. Notice we start with a blank slate. This is the perfect place for mathematics to begin. And then we drew a box, because we're dealing with drawing boxes. We have a box. It has a height, base, rise over run. We also have a characteristic diagonal, right? Pretty simple. Inside this box, we drew a general purpose shape, an amoeba. You've seen amoebas? Doesn't it look like an amoeba? That could be a COVID-19, you never know. Okay. Well, anyways, this amoeba has, obviously, it has some kind of an area, and at point P, well, it has some kind of a slope, right? So, that was ugly. And things are kind of changing everywhere, it's hard to tell what's going on. But our approach to finding the area and the slope is based on what we call invariant, or more specifically, isoratiometric invariant. So let's see what we have here. There's our amoeba, and notice we're always thinking in terms of the box. Take any point like point P on this amoeba. Drop down vertical, a horizontal, and a diagonal. Okay, that's your box. And now look at this thing. We have a ratio of this. This is the tangent to the diagonal. And notice that if you move to another point, that's a different ratio, right? This tangent to this diagonal is different from the tangent here to the diagonal here. See that? They're not the same. Of course, if you were to stretch the amoeba like this, well, at this point, and at this point only, the ratio of the tangent to the diagonal is the same as the ratio of this tangent to this diagonal. It doesn't change, it's invariant. But it's invariant at only one point. It's a different situation when you move to point Q. Here, yeah, you got another ratio, and it's the same ratio as you stretch it, but it's different from P. And the same goes for the ratio of the area, inside here to the box, compared to the ratio of this area to this box. This is the same at point P, but it's not the same compared to point Q. That's a different ratio of the area. So even though they are invariant just at this one point, they're not invariant everywhere the same. But there's a special curve called y equals x to the n. That is, let's take a look at simple point y equals x squared. So we draw it like this. And my setup is basically from 0 to a to 2a. And so, therefore, since this is an x squared, this would be a squared, this would be 4a squared. Okay. Let's look at this point here. There's a tangent right here. The ratio of this tangent to this diagonal let's do some stretching. Rubber band geometry. Can you give me a rubber band? I've got to have a rubber band. That's always a must. Since I mentioned rubber band geometry, I need to have a rubber band. Okay. Basically, what we are going to do is take this point here, point P, and stretch it. And here's a rubber band. And unfortunately, it's got some writing on it. I don't know if you can see it. Can you see this? Is it focused? Can you see the writing on it?
Kinda.
I don't know. I wish I had it better. Move it closer or further.
It's not focusing.
Oh well, you do your own experiment. Get a rubber band. There's some writing on it like asparagus, produce of Mexico, whatever. And just stretch it. Now we got a better rubber band. Let's see. Can you see this one? This one says produce of Mexico. See it? Yeah, that's rubber band geometry. Everything stretches. If you have an honest rubber band, it will stretch equally, right? Of course, that's kind of a hard thing because the thickness will affect how honest it is. Okay, but imagine this. Here we have this setup, and here we have this wedge, and we simply take it and we stretch it from A to 2A. So effectively we have doubled this area, right? On the wedge, this to this. But we've also doubled this rectangle here. So the ratio of this new wedge area to the new rectangle is the same as the original wedge to the original rectangle. And now imagine pull 4 times up to point Q. Okay? Well, guess what? You're going to end up at point Q. And you're going to have a point right here. It's going to retrace the original curve because this point P has to be 1/4 of this height here. So look at this. Here we have a new setup with point Q. We have the ratio of this slope to this diagonal is the same as this slope to this diagonal is the same as this slope to this diagonal. Also the area. This ratio of this area to this rectangle, same as this area to this rectangle, is the same as the big wedge to the big rectangle. It is invariant. For x squared, it would be K2 for area. That's the invariant, the ratiometric invariant. And C2 would be our slope ratio. And it's one value, which is different from this situation here. Here, it varies all over. This one, same invariant. This is the secret sauce that makes it all work. So, you pull it, it doesn't matter. Even if you pull it, just like you pull this one, it's still, you start out here. Oh, let's say you pull it, it's still the ratio of this to the characteristic diagonal, same as this slope to its diagonal, same as this tangent slope to this diagonal. It's C2. And the same with area. The ratio of the wedge area to the rectangle, same as this blue wedge to this rectangle, same as the overall to the overall rectangle. It's K2. One value. ISO ratio. ISO means same, like isometric. Well, it's isoratiometric. That's the secret sauce that makes quadrature work. And to prove it, consider a simple curve like this. Y equals x squared plus 1. Yeah, it's almost looking like this, right? It's just offset by 1. But notice, this is not isoratiometric invariant. Look at point P. Here we have our tangent slope. Ratio of this to the diagonal is not the same as this to this diagonal. You see the difference? Clearly different. Not the same. What does that mean? You can't do quadrature. Same with area. Look at the area that's underneath this curve to the area of the box. Okay, it's approaching 1. It's slightly less than 1 as you're close to here. But now let's say you move away. It's different. Over here, the ratio of this area underneath the curve to the box is different from the ratio over here underneath the box to this box. It's not isoratiometric invariant. Just a simple x squared plus 1 means we can't do quadrature as it is. Ah! Don't cry. We can take advantage of the additive principle of areas. Areas can add and subtract. We basically split this up. Take scissors, snip that. Now you can do area, right? This is just a rectangle. Easy. How about this one? Well, that's just your x squared. And we found out that K2 is equal to 1/3 and C2 is equal to 2. Actually, we have found that K sub n equals 1 over n plus 1 and C sub n equals n. We have found that out. And that's in these past videos. And that is hot stuff. And so, how did we do it? Let's kind of review. Let's do a review here. Okay. Well, let's review. Basically, here's my setup. And it looks something like this. Yeah. And I'm doing y equals x to the n, right? I'm actually drawing it for y to the x squared, but that's okay. So there's that. There's the diagonal. 0 to a to 2a on the x-axis. And using translation on the t-axis, 0 minus a. So we get 0, a to the n, 2a to the n. See that? That's our basic setup. And with this, we found an interesting property about these things, which I call kind of a theorem of quadrature proportions, that these areas of the function itself, as well as the slopes of these functions, as well as the little areas, that are all governed by the binomial theorem. Go back to the previous slides or previous videos and study that. I think they're lovely. But that's kind of my setup. But I found that using Professor Weilberger's setup was even better for finding these k to the n and c to the n. And here's his setup, which that conforms to his video famous math problem 10AB. He kind of sets it up this way: 0 to 1, 1 plus c on the x-axis, and with translation we're going to use a t-axis, which is superimposed on the x-axis. 0 to c and minus 1. See the difference? Here our basic translation is x equals a plus t. That's my setup. So when t equals 0, x equals a. When t equals a, x equals 2a, etc. In Weilberger's setup, you say translation is x equals 1 plus t. When t equals 0, x equals 1. When t equals c, x equals 1 plus c, and so forth. And so y equals x to the n. All right, well, let's set this up. If y equals x to the n and x is 1 plus t, what does that mean? Well, it means that y equals 1 plus t to the n, right? Just plug that in. Okay. Let's see what we get. So we say y. Well, that equals 1 plus nt plus a whole bunch of binomial junk plus, well, let's just call it, what do we have? T to the n. That's all we need. Okay, not bad. All right. And so what's the slope? And particularly, whoa, I need to draw my curves, don't I? Ugh, isn't that ugly? Okay. So there's 0, 1, 1 plus c to the n. All right, you see that. Okay. Well, the slope, well, slope is the slope of each of these little functions, right? Because slopes add and subtract. And from the x perspective at t equals 0, well, what would we have? We would have this. C to the n, the slope. Well, we're after c to the n, the slope ratio, and k to the n, the area invariant isometric ratio. But the slope is c to the n times 1 rise over 1. run. See this one from the x perspective? At t equals 0, which is x equal 1. What is the slope of this thing here? Well, that's our c to the n times rise over run, 1. Okay, that equals, well, that's the slope of each of these functions. You're going to have a constant, a linear, a quadratic, a cubic, up to t to the n. And we've shown that, you know, the only function that gives you slope is really the linear function. Any other curve, you can see this would be t squared. At t equals 0, the slope, it has to be 0 by symmetry. It's a symmetry argument. And that's that'll be t squared. What about a t third? Well, we know that t third comes in underneath like this, and then of course it goes like this. But we can use sandwich theorem, or whatever you want to call it. And so you can see that it has to be 0. The only one that contributes is this one. What's the slope at t equals 0? The linear, it's n, clearly. Equals 0 plus n plus 0 plus dot 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 plus 0. Because all of these functions, their slope is 0 at t equals 0. The only one that contributes is your linear function. So you can see that c to the n is equal to n, just like that. C to the n equals n. Nice. All right. Love it. With one setup, we're doing slopes and areas. Boom. So let's do the area. Okay. Or the area factor. We're after k sub n. Okay, from the x perspective, the area of this big wedge right here, right? That would be k sub n times 1 plus c rise times run, 1 plus c to the n times 1 plus c, right? So it's really 1 plus c to the n plus 1, right? Times 1 plus c. Well, you might as well just say n plus 1, right? It's one more power. Okay. Well, that equals the area of these little functions over here. Plus, don't forget, this little wedge over here. Got to pick that up. And then the little functions that make up this funny looking wedge here. So let's go after this one. And that is simply, well, that's k sub n times 1 times 1. I mean, that's just k sub n. Right? Times 1. So that was easy. That's just k sub n. Plus the areas of each of these little functions that you get. And there's a whole bunch of them. And look at my previous videos. And you'll see them. They all add up. Okay, so the constant term, well, that's simply c times 1. So that's really c plus, and we really don't care about the others that much, dot, 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 until the end, in which case we get the last one for t to the n would be k to the n times c to the n times c, which is really k sub n times c to the n times c. So that's going to be a c to the n plus 1. Let's crank this through as much as we can, right? So it's k to the n times 1 plus n plus 1 times c plus a whole bunch of stuff plus c to the n plus 1. Okay? And that equals the stuff on the right. K sub n plus c plus a whole bunch of stuff that doesn't matter plus k sub n c to the n plus 1. And we're going to have some cancellations here, namely this 1 with this one, see, k sub n times 1. And also k sub n times c to the n plus 1, this one cancels this. Notice the only thing left is this one. And you're going to have c terms, c squared terms, c third terms, a whole bunch of terms that are redundant. Go back to my previous video. And so this is simple. Look, k sub n times n plus 1 times c equals c. And look, the c's cancel out. K sub n equals 1 over n plus 1. That's simple. 1 over n plus 1. We're using Wahlberger's setup, and it is so simple. One setup, we do slopes. One same setup, we do areas. The simplicity is just amazing. That's what the invariant does for you. Okay, that's the power of the invariant. Notice we're not relying on this thing called limit, which I'm not saying it isn't there. It is there, sure. Now, how would you set up? How would you do Cavalieri's principle without the limit? I have no idea. I work through the invariant, and that's so simple. I mean, one setup, there it is. We are relying on Wahlberger's scaling properties of areas. I think he's got 5 of them. Well, what are they? Additivity, linearity, translation, that's this thing. Dilation, that's rubber band. And normalization, which is kind of what these are normalized. Anyways, pretty simple stuff. Look, we proved c sub n equals n, k sub n equals 1 over n plus 1, almost like that. That's how simple it is. What can I say? That's the way to do it. Also, we talked about notation. And we said for slope and area. So for area, I'm using this thing called S, which stands for signed area of, let's say, x to the n. Well, that equals, it's an operator, a box operator. Literally, we're talking the box times k to the n. Right? So it's k to the n times x to the n times x, which forms a literal box. Height times base, which you can look at it also as k sub n x to the n plus 1, right? Raised by 1 power. The slope, tangent slope, at some particular point, let's say over here, there's point P, and it could be parameterized as x to the n and x. That's what point P is, right? So slope, we call it the box operator D, right? D of x to the n, right? Well, that equals C sub n, this thing here, times x to the n divided by x. And that equals C sub n x to the n minus 1, lowered by 1 degree. And that's our basic notation that we use. And I like this one because this retains the units. If this was kilowatts and the other one was hours, the area would be in kilowatt hours. And here the slope, if we had volts per meter, well, that would be the units of our tangent slope, volts per meter, electric field. So this is great stuff. Think of it this way. Literally think of it as a box. Think inside the box. That's the key. Okay, so I think we're going to wrap it up, and hope you enjoyed it. Yeah, I hope to have a lot more videos. So, I'm Professor Theoremus Antiquitus, also known as Invariants.